Hello everybody. In this video we're going to start the new chapter, which is chapter number 8, which is very related to what we discussed in the previous chapter, which is the calculation of enthalpy or finding enthalpy for non-reactive processes. We mean by non-reactive processes the processes that do not include any chemical reaction. The reactive processes would be included or discussed in chapter number 9 after we finish this, inshallah. So for this chapter, we are going to build on what we started in the previous chapter, and that's why I would like to start this chapter with a quick revision to some of the very important or basic concepts that we need to keep in mind before we start what we are going to go through in this chapter. These are really important things, and we have to make sure that we fully understand them and we have them clear in mind before we start anything. Because this is the basic thing that we are going to build our discussion on. So let's start with the equations of energy balance. We had two types of equations for different types of system, for closed system and open system. The main difference here is the enthalpy for open system, which is a replacement of internal energy or the substitution of internal energy in case of closed systems. And we have the kinetic energy, potential energy, Q and work. They're all the same, but this work is shaft work. This is shaft work as well, but we call it shaft work because in open system we have another type of work, which is the flow work. And we have gone through all these details before, so I'm not going to waste more time in this slide. For the next point is the reference state. We talked about this in details before in chapter 7, and we said that we cannot calculate the enthalpy or the internal energy, the absolute value of the internal energy or enthalpy, because we cannot measure the actual value of the internal energy and accordingly the enthalpy. So we said we cannot calculate the absolute value, but we can calculate the difference between two values. And to do this, we said we have to set a reference state and for our reference point. And for this reference point is what we consider the enthalpy is 0. And we calculate the two enthalpies, H1 and H2, relative to this standard enthalpy or the standard state. So this is what we calculate as the difference in or H1, which is not the actual value, it's the value with relative to the reference state, and the same for H2. This reference state is state of the matter at a specific temperature, pressure, and phase. This is what we consider. And we said that the reference state doesn't matter, the difference will always be the same. So if we set another reference state, then we will have the same difference, which is, or the two enthalpies will be different, of course, but the difference is the same, which is this difference. So it's either calculated as H2 minus H reference 1, which is this, minus H1 minus H reference 1, which is this, which will give H2 minus H1, or H2 minus H reference 2, which is this, minus H1 over minus H reference 1, which is this, which was also will also give us this. So what we learned from this before, that the value of delta H is the same regardless the reference point. And for simplicity, or to make our calculation simpler, we said that the standard the reference state will have 0 enthalpy. This will make our life much easier. So this is what we said before. For the previous chapter, when we wanted to calculate or find the values of enthalpy, we used steam tables, and in steam tables we discussed this before, that we know the reference state of the steam table, and we said steam table is a very simple method of finding the enthalpies. We just look up the table and find the numbers, and we said that the reference state is the triple point of water or liquid water at triple point, which is has 0 enthalpy, 0 internal energy, which is at 0.01 Celsius, 0.00611 bars. And we said that the and this is what we need to know about the reference state. It doesn't matter if we have water in, water out, then we don't care, because the reference state is the same for both. So and we were asking at the end of the last chapter, we were asking a question: what if we have something else other than water? How can we deal with it? Before we answer this question, I want to give a very quick example. We solved examples like this before in chapter 7 of using steam tables. And in this example, we have liquid water at 10 bars and 75 Celsius, and it's being heated to 300 Celsius at the same pressure, and we want to calculate the change in enthalpy. So simply what we do is we want to get H2 and H1, and in this case H2 is the enthalpy of water at 300 Celsius and 10 bars. H1 is the enthalpy of water at 75 Celsius and 10 bars. So we will go to the table. This is, I just cropped the parts of interest. So this is 50 bars, this is 75 bars. So this is the enthalpy, H1, and this is H2, 300 Celsius. So it's as simple as this. You go to the table, pick the numbers, and you find the difference of enthalpies. We did this more than once in the previous chapter, so this is not new. But the point that I want to refer to here, which is a very, very important point, that there are things that we didn't even think of. When we use the table and extract the numbers of the table and the numbers from the table to calculate the change in enthalpy, we didn't even care about the difference between the phase of water at state 1 or state 2 and the phase at the reference state. And what I mean is that the reference state is liquid water. I didn't care if I'm calculating or picking up the value of enthalpy of vapor or liquid. I just go to the table, pick the number. It's none of my concern. And you might be surprised why I raised this point. I'm raising this because it's going to be a point of concern later. So you need to appreciate what the steam table is offering for us. So steam table is giving us the enthalpy data ready to be used, which is a very, 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 very big time saving thing, that you can just pick up the numbers from the table and use them directly without worrying about anything. So this is a very, very big advantage of using the steam tables, and we will see how this will make a lot of difference when we do the calculations for other materials. So this is a point I want to make clear, that in steam table you don't even think if the water that you are using or the number that you are picking from the table is for liquid or for vapor, or is it different from no, it's not care about liquid or vapor. Of course you care, but I mean if the phase of the water is different from the phase of the standard state or not. You don't even think about it. So this is a very important point. The second point is that you don't care if the two states that you are calculating the enthalpy for, which is H1 and H2, if they have different phases or not. So here it's liquid, here it's vapor. You didn't even care if there is a difference here. You just go to the table, pick up the numbers. As long as you're picking them right, you're done. This is all what you need to do. And it's a piece of cake here. You just pick the numbers, put H2 minus H1, and you're done. You calculate the difference, and it's done. So this is a very, very important thing that the steam table is offering for us. The difference in the phases is not a big deal. It's not a deal at all. So it's not something you worry about. And now we want to know if this is the case for other compounds or it's going to be different. So let's do the same thing for other materials. So now let's say I want to calculate the change in enthalpy for a process where solid phenol, it's something other than water. So it's solid phenol at 25 Celsius and 1 atmosphere is converted to phenol vapor at 300 Celsius and 3 atmosphere. So what we would think is that if we have the table of properties of phenol, and if there is something that's called phenol table, like the steam table, you would do exactly what we did before. You just pick the two enthalpies and then get the enthalpy 2 minus enthalpy 1, and that's it. It's as simple as this, if you have the table. And this is the problem, and this is the question. There is no phenol table. We don't have this kind of thing. There is no way we can find table of properties of phenol, and we don't know how to get the enthalpies of H1 and H2 by just going to tables and finding them. So the option that we have is to calculate them. And to calculate them, we need to go into some details that we went through before. Is what are the steps that the material goes through between state 1 and state 2. And you are going to follow the same path and calculate the enthalpy change for each step that the material went through. So just to remind you, we said before that for solid ice to turn into water vapor, it goes through different states. So first, it takes some enthalpy or energy to turn into saturated or solid at the melting point, and then it takes H2, which is the latent heat, to turn from solid to liquid or for melting, and then it takes sensible heat to turn from saturated or liquid at the melting point to liquid at the boiling point. Then it takes enthalpy to turn from liquid at boiling point to vapor at boiling point, and then it takes enthalpy to turn into superheated steam. So this is the total enthalpy change, is the enthalpy it takes for each one of these stages. So the total enthalpy difference between this state and this state is the summation of all these enthalpies. It turns from solid into the solid that is about to melt, and then from solid to liquid, and then from liquid to vapor that's about or liquid that's about to evaporize, and then from vapor to liquid or vapor liquid to vapor, and then from vapor to superheated steam. So we can calculate the enthalpy at each one of these steps, and we can calculate the total enthalpy change by adding all these enthalpy differences. And now you can appreciate what the steam table is doing for us. In steam table, you didn't even care about all these things. You just pick the enthalpy here and the enthalpy here, and you are done. It's as simple as this. But when you do the calculations manually, you have to go through all these steps one by one, which is not a very fun thing to do. So there is one more thing that we need to remember, which is that the enthalpy and internal energy are state properties. We mean by state properties that they are properties that depend only on the current state and conditions of the matter. For example, just to remind you, we gave two examples of liquid water. One of them was ice that melted, and one of them was vapor that condensed. And we said that both samples are at the same conditions of phase. They are liquid at the same temperature, they are at the same pressure, they are pure water, so they are almost the same, but they came from two different conditions. And we said that the enthalpy of the two samples is going to be the same. They have the same enthalpy and the same internal energy. We don't care about the history of this material, we just care about its current conditions. And this is what we mean by state properties. And this is a very, 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 very important thing to keep in mind, because this is what we are going to build all our arguments or our calculations on until we finish this course for chapter 8 and chapter 9. Knowing that the enthalpy, the state property, so we want to calculate delta H. So to calculate delta H, we have state 1, which is the solid phenol at 25 Celsius and 1 atmosphere, and then we have the vapor phenol at 300 Celsius and 3 atmosphere, and we want to calculate this delta H. Since this is a state property and this is a state property, so we don't care about the path that we take from here to there. So if we can calculate it with a single stage, then it's fine. If we can break this into different stages and then get the summation of the stages so that we can get the difference between the enthalpy here and the enthalpy here, it's also going to be fine. Again, because this doesn't depend on the previous history. It doesn't matter how you reach at this point. As long as you reached it, then it's fine. The same here. And this is what we call by a hypothetical path, that we will come up with steps for changing enthalpy from here to here. And what we're going to do is we will calculate the enthalpy difference for each one of these steps until we reach from here to there. And again, this is what we said here, that we cannot calculate the enthalpy difference from here to here directly, so we broke this into different parts. So this is what we are going to do here. This is what we call the hypothetical path. So here, this was a hypothetical path. We call it hypothetical because we don't know if this is what happened or not, but this is a path that is a possible path for the solid to turn into vapor. So this is the same here. It's a path that this solid could take to turn into vapor. So I hope this point is clear. So You just imagine what would be the path. We have here 25 Celsius solid, and at 1 atmosphere we have 300 Celsius vapor at 3 atmosphere. So the hypothetical path that we are going to go through is a path that consists of steps. Each step is consists of only, or represents only one change. It's only one change. So we can say that the first step, or the first change, is that this solid phenol turned from solid into solid at the boiling point at the same temperature, at the same pressure. So we change it at the melting point, I'm sorry. So we change it only the temperature. Then we'll have another step where this solid is going to turn into liquid at the same temperature. So this is latent heat. Then this liquid will take heat to turn into liquid phenol at 181.4, which is the boiling point. And then it's going to gain more heat to turn into vapor phenol. So it's now saturated vapor. So this is latent heat. So it's turning from saturated liquid to saturated vapor. And then we are going to heat it more to turn it into vapor phenol at 300 Celsius and 1 atmosphere. And then it will be vapor phenol at 3 atmosphere at the same temperature and higher pressure. So we are increasing the pressure. So we call it a hypothetical path. And now we can tell that this green enthalpies are latent heat, the blue enthalpies are sensible heat. This blue dotted lines and all these blue circles, this is what we call the hypothetical path. We call it hypothetical path because the change could have happened in a different way. It's just a hypothetical thing. For example, you can have the path going or starting by changing the pressure and then changing the temperature. It's fine. In the actual process, you might have the temperature and pressure changing simultaneously. So you're not actually doing or representing what happened in reality. You are representing a possible path that could the material could go through to turn from solid into vapor from these conditions to these conditions. And what is important here, that you are making each one of these steps a step that includes only one change in the parameters, either the phase, either the temperature, either the pressure. This is what we call, and we will see later why we do the hypothetical path this way. And we will, if we can calculate the enthalpy, each one of these enthalpies from delta H1 to delta H6, we can say that the total enthalpy difference is the summation of all these enthalpy difference. So it's delta H1 plus delta H2 plus 3, 4, 5, and 6. So it's exactly what we did here. We said that this is how we broke the enthalpy change from here to there into steps. So it's exactly the same thing. We said that the enthalpy change from here to there is the summation of delta H. So we say here also that from here to there this is the delta H that we can go through. So this is an important thing to understand, because this is what we are going to be doing from now until we finish the course. So this idea must be very, very, very clear. And it has also to be clear that this is possible because the enthalpy here and the enthalpy here, they are both state properties. It doesn't matter what was the previous state. It doesn't matter how we reach this point. Meaning I can do another hypothetical path and still get the same result as long as the path is fine. And for example, I can make one step where the temperature and pressure are changing. If I can, I can do this, but I cannot do the calculations. But I can do this. So it doesn't matter what shape of the hypothetical path you are going to use. It matters that the path is a valid path. As long as you can calculate each one of these segments, then it's fine. So this is a very, 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 very important concept that we need to understand. So I'll stop here and we'll continue next time, inshallah, and we'll understand why we use this hypothetical path in this way. So I'll see you next time, inshallah. Goodbye.